Hmm? Yeah, the big fat minima. Mm. Ye- Yeah, the slide for that I have is here, is this sharpness aware sin. That's the fat minima sin. Yeah, I don't know how much it works. No, don't spoil it for yourself. Why do you like browse all the slides? So the deep learning enthusiasm diminishes ever continuously. Um, okay, so today it's gonna be like a little bit superficial coverage of different vulnerabilities in deep learning, but it's fun topic. We can enjoy the talking about this and discussing these things and seeing what are the vulnerabilities and so on. So as the introduction, like we have these great machine learning models that are reaching the superhuman accuracy on the image classification, right? And we also discussed about that they were inspired by the neuroscience, by the organization of the visual cortex and so on, and that we really find in these convolutional neural networks some kind of phenomena that are similar to what we know from the human vision and what we would expect, what looks natural to us as humans, what these networks could do. In particular, this first level filters, they are similar to Gabor filters, which is kind of computational models for the what is happening in the eye, and then there is some evidence of kind of hierarchy of parts processing that the neural network at a deeper features it builds more abstract. It is able to react to some kind of part concepts, and even if especially so it is not trained to recognize these parts, but it emerges as a kind of intermediate step for it to perform this places recognition. So it discovers that okay, it is useful to have some units which are detecting this part, and this kind of agrees with our understanding, and we like the performance, but so these are all on the good side, but there are still so that's not the whole story. So there are some things on the unexpected side, right? On the side which just does not agree with human vision and for which is maybe counterintuitive and unexpected different kinds of vulnerabilities. I don't have like a special slide for that, but one thing here is that so this superhuman performance, this is in the setup when you have a training set and a test set. Not exactly the same, but in many respects sort of obtained with the similar methods, and in many respects like similar collection of images. What I mean by that, so I want to talk about the change of the distribution. Once so you train on some training distribution and then you test it, and then the testing distribution might change. It might change in the way that is kind of a significant change from our human perspective. And then, yes, we can say, okay, so what? It will perform worse because, yes, so these classes are represented by very different proportions, or the appearance changes a lot. If you were not doing something specifically for that, it is sort of reasonable that the network does not generalize to that. But it may change also in some like subtle ways, which is unnoticeable for us, but the network performance suddenly drops. And this could be things like, okay, the images were compressed using a different JPEG algorithm. So you don't notice anything, but suddenly the performance drops. Or it would be, so our colleague Vladan is working on the representation learning. So then they are working with these big models trained on very large collections of images. And they discovered something like, okay, the model that was trained on the data which was collected before a particular year, it was not including the images taken by newer cameras which were manufactured afterwards. And for some reason on the newer cameras, the model is picking up something that is correlated with the fact that this comes from the newer cameras, and then it spoils the retrieval, so it spoils the performance a lot. So somehow, and so cameras these days are now, they include, it's not only photometrics, it's not only the lenses, right? It's also all the computation from these micro sensors, and then this processing of these Bayer masks and the denoising and all kinds of filtering to enhance and sharpen the image. So who knows what is different in these images, but yeah, it represents some kind of unperceptible to us distribution shifts to which these networks not necessarily generalize or may fail to work well on that. So yeah, here is another question. So we touch this in passing. It could be like a deep topic on its own, but let's just consider this together with the other vulnerabilities. We are training these classification neural networks as probabilistic predictors. So they output predictive probabilities of each class given the input. And often you see some images like, okay, this dog, and this is 0.97 confidence, or this predictive probability that this is a dog. And yeah, so the networks are capable of, we can read off from this probabilistic predictor also this confidence. But what is the meaning of this confidence? The theory tells us that if you have enough data and the model is well specified, then it is the negative log likelihood is a proper score. That means that in the limit of enough data, we will be learning the true conditional distribution of images labels given the image. But in practice, we don't have that. So in practice, we train on the data which is more or less from the image. You could more or less unambiguously tell its label. It could be some human errors, like, okay, so if it is very fine-grained, breeds of the dogs and species of I don't know what, there could be some confusion in the errors, but you don't expect confusions between like a bird and a cat, right? So these labels are more or less unambiguous in the training data. It is possible to predict them for a human to label that exactly. So there is no real distribution over the labels in the training data, and it makes sense to fit this data completely to train the network that is performing 100% accurate on the training data, right? Why not? If we have clean labels, so then we would expect that. And then, I mean, regardless whether the labels were correct and clean, if we are training these over-parameterized models on some limited training data, we are often in this mode that we can achieve the zero training error rate. And then what we can expect about this predictive probability distribution. So then we are kind of in this picture that these are some classes, and then we are finding some good classification boundary, but the predictive probability, so these probabilities, the longer we train, the sharper this will become. So it will kind of very confidently say the class label, so very confidently will predict one of the classes. And yeah, that's what observed in practice if we have, especially on the smaller data sets like these CFR data sets. This is some ResNet networks. Right, what these diagrams are showing is like comparison between the predictive probabilities and the real accuracy. So what I have in this example is that, yes, you have the bird and it's labeled as a dog. Right, that's wrong for us, that's obvious for us, that's not a dog. Maybe it was not obvious for the neural network, and it was quite confident that it is a dog. Is it a problem in itself? Not necessarily, right? So people also make errors. So any predictor or system will make errors, and people also sometimes could be overconfident. The problem would be only if you are overconfidently wrong and you are doing this often, right? So if this type of prediction is happening too very often, so that this confidence, it must correspond somehow to the accuracy of your prediction. So if you are predicting accurately on average, then you should have like corresponding high confidence. That would be reasonable and expected. If you are all the time wrong but still overconfident, then that's still high confident, but that's a problem. And these diagrams, they are measuring this sort of thing. So on one axis, there is this confidence and prediction, and on the other axis, the accuracy. And for this confidence to really be meaningful, it should correspond to the accuracy. So so the calibrated model would have this diagonal graph. And if the confidence is, let's say, 0.9, but the accuracy is 0.6, this means that the model is overconfident. So it is more confident than its real accuracies. And so you have this outputs under this curve, and then this indicates like overconfident model. Yeah, so there is like this metric to look at how this confidence agrees with the accuracy, but it's only for the probability of prediction of the most confident class. So if you care about other probabilities, like you want to use this whole probabilistic model for, let's say, Bayesian decision making, or for adapting to the change of the distribution, like if you want to use all these probabilities, then you care not only about the probability of the best of the top predicted class, but about all of them. So then these calibrations are not enough, and then you need some more detailed calibrations and metrics. There are methods to rectify this a little bit. They are not very difficult. So specifically, you train like a post-processing of these predictive probabilities, which has not so many parameters, so that you could, given like some additional calibration data, you could fit these few parameters such that to make these curves more aligned with the calibration model expectations. So usually, yeah, so you could either this, or the other side of this is that, okay, you are getting these overconfident models and poorly calibrated models, especially in this mode, but when you are training for very long and it's separable. So the natural thing is that, okay, let's use more data augmentation, more regularization, and then this will not be happening, so it will not go into this mode of training the overconfident predictors. And then maybe the most recent and larger models trained with more data are, they have less of this kind of problems. Okay, so these predictive probabilities somehow could be addressed. But then there is another thing, the adversarial examples. We discussed a little about these JPEG artifacts, right, or the dependence on the camera. And then people tried to see, okay, actually, can we find the small perturbation of the image which deliberately confuses the network? So not just by accident that it is some JPEG artifacts, but okay, we're gonna really optimize for what small change of the image would fool the network the most. And there are several techniques. I mean, we will view it later on as optimization problem, but to start with, we just, we have some image, and we know the network and the loss function. And we do like a change of the image in the direction that increases the loss the most. So we take the gradient of the loss with respect to the image, not the parameters, but respect to the input image, and change this image a little bit in that direction to change the loss the most. And it turns out that this change itself, so this step, looks like some kind of noise. It's not a random noise, it's structured noise, so it's spatially somehow correlated. But a small amount of this noise so is sufficient to be added to the image, such that, okay, you see the same image, or anybody, but the neural network sees something else. So it completely confuses the output, it completely confuses the prediction, so it will be with very high confidence predicted as some other class, right? So that's unexpected to us, so we would say that, okay, there is no noticeable change, nothing like different elimination or different complicated viewing conditions. We don't see anything, but then the network gets completely fooled with that. And so this is for classification. Then you could do this. So the semantic segmentation is like classifying at every pixel, right? So you could play this trick with semantic segmentation as well, and you could not have the goal not only to break the current prediction of the network, but you could even like what is called targeted attack, that you would like to find a small perturbation of the input image such that the prediction at every pixel will be the one that you like, not the one that is the truly there, but arbitrary something that you like. So these are like the input image, the original semantic segmentation, and then somebody said, okay, I want the network to make this segmentation from the input image like this, but maybe perturbed with a little bit noise, which we do not see. And it's possible, right? So you add a little bit of adjustments all over the place so that it's not visible to us, but the network then produces this. I don't know what's that. Hello Kitty or what? Or it produces like a completely segmentation, like arbitrary semantic segmentation of some other thing. And this now looks quite dangerous. So it indicates on one hand, it indicates that somebody could be doing this on purpose to somehow, I don't know, if it is the driving scenario, somebody could add some kind of particular patterns or the noise printed on the truck, or feed the images somehow with this additional noise to the system, so that it will be some danger. And the other side is that, okay, it tells us something about the neural networks, that they are sensitive to some directions in the input space to which we are not sensitive, and we would like the networks also not to be sensitive to that, because these directions are kind of not important. Yes, they are not occurring in the nature, so these patterns, so they are like specifically structured, so this is never observed in the nature, so it would not kind of affect the performance of the system in the nature. And yet the fact that the network could be very sensitive to these unnatural directions is undesirable. So we would maybe in the natural statistics, if you compute a particular correlation and the deep processing, then the things cancel out because of the natural statistics, not so somehow independent in that respect. But in the neural network processing, so if normally they cancel out, but if they are kind of with the purpose adjusted on the input, they are not canceled out, but kind of amplified. And then this allows, with a very small perturbation, to achieve like a very big difference in the response. And maybe that's not good, so we would like to have some invariance to that. But, for different purposes, for security, for better interpretability, for better generalization, maybe.
Has there been some research into like maybe generating these adversarial examples on the fly during training and using them as sort of data augmentations to try to?
Yeah, yes, this is the right thinking. There has been such research. You'll come to this, so this will be the second part. Yeah, so okay, maybe one possible illustration to somehow get a grip on what is going on with these adversarial samples is that, okay, so this illustration, so suppose you have some manifold of the images in the space of all the RGB pixel coordinates, and then you have two classes, and you want to classify, and okay, maybe some good classification would look like this and stable. But what happens is that our models, maybe they are producing such a decision boundary which is like fairly close to this manifold in some spaces. So like a little change, like little perturbation from this example will turn out to be on the other side of this classification hyperplane. Yeah, this is limited interpretation because the distance in this space is meaningful, and this space is like lower dimensional. What happens in reality is that the input space is much more higher dimensional, and the distance in the pixels is not necessarily so the distance in the pixels still captures something. That's okay. What is the difference is that the classification is not really happening in the space of the pixels. Okay, it does happening in the space of the pixels. It just there is some discrepancy. So I was often drawing this picture and saying, okay, for linear classifiers, we understand it is going towards the maximum margin, but this is in the contradiction, right, with these adversarial things. If it was really the maximum margin separating hyperplane, there would be no adversarial examples. The issue is that this maximum margin property is in some lifted space of some reproducing kernel Hilbert, I don't know what. And so if it is projected back into the original space, then there is no more the maximum margin with respect to the metric in this original space, and the decision boundary could be kind of quite complex, maybe, yeah, like this, or maybe very complex. Yeah.
I'm still puzzled by this, yeah, but this is like, it seems to
Me too.
all adversarial examples I have seen are kind of some low-level noise, yeah, which is something we are not sensitive to, like as humans, but all neural networks, probably all, are still sensitive to it. And I haven't seen something like high level. If you want to fool humans, you have to do some high level structure stuff or something, and it's not so easy. So like, yes, this is maybe one explanation. The other explanation is that, and something we are maybe still missing, I don't know if there is an answer for it, like how to avoid this focus on these low level features and focus more on something semantically meaningful, high level. And I don't know if we have answer for it actually, but this is like common theme to most of these attacks. And
no, for us there are also some things like some kind of optical illusions when you see things are in agreement, but it is just a result of some accidents. Indeed, yeah, and that's why this is like most counterintuitive and strange about this. So there is this small noise, but there are also these adversarial patches. We will have some pictures. But they are also, it's not like realistically confusing scene, which would be normal, right? It could be. So if some things are looking alike, or you are confused by the perspective or by something, so or okay, the human vision has some other things which are different optical illusions that it may seem that something is rotating to you and so on because of the specific patterns.
from our example, it's possible to have such a system which is robust to this.
Yeah.
We still don't know how to build it. Yeah? So maybe this is still like interesting.
Maybe the goal shouldn't be to make it behave same as the human visual system, but to make it behave like properly for the given task. Because, for example, like some optical illusion with perspective could be also a very bad thing in like a self-driving application or something. So
Yeah,
I
indeed.
feel like there will always be some trade-off, and it's just like meaningful to.
Maybe you can have both. Yeah?
Indeed, yeah. If you could take the point of view like, okay, these things are not happening in the nature, then why should we care? See if the camera is then.
That's not what I'm saying. No,
Yeah.
I get it.
Well, I am also not what I'm saying, but it is one one side of this. The other side of this, yes, it is still telling us something about generalization and about this unwanted directions in the space which cause substantial effects, and it could be indeed mm, some interesting effects, consequences, even if this is applied in the society. Okay, yeah. So let's look at a little bit at how these methods work mathematically. So we discussed, okay, so we have some loss function, and we look at the loss, let's say this is be the logarithm of the softmax loss, and then we can have the basic thing is called fast gradient sign method or fast gradient sign attack. So we take the true class label, look at the loss of the true class, and compute its gradient and make a step in the in the direction to increase this loss. So if the network was predicting the true label, then making the step to increase the loss. After that, maybe on that perturbed image, the network will have the very high loss, and then it will probably not be the true label. So that would be like a cheap and one-step attack, or we could make it iterative. So we could repeat this procedure, and but still, like if you want to keep the noise perturbation to be bounded, so then we would need to have some projection step to say that at every iteration we kind of project to the constraint that the noise is not larger than the allowed perturbation, so that it is not noticeable. So this is like roughly, maybe let's look at it at more detail as like solving this optimization problem. And so we fix some norm on this noise. So we want a perturbation to the image that it is not more than something in particular norm. So in this case, let's take the norm, which is the infinity norm. So it is a maximum perturbation in every pixel. So in every pixel, it cannot deviate more than, I don't know, 3 levels of the color value. So then we have the loss with the true label. So let's denote it as the f of x, a function of the input image. Then what we do, we linearize this loss function at our current input image, and we are looking for the perturbation to the input image such that this linearized loss is maximized. And this is related to this trust region problems and the proximal step problems. So when in the optimization, so maybe in the next lecture we will look at this trust region problems as a way for adaptive optimization. So here it is in the space of the input images, and this infinity ball is kind of a box in the space of the input image. So essentially you have the loss function, which is represented by these level sets, and you have your input image, and within this box of the input image you want to find a point such that it maximizes the loss, right? So we solve such a constraint problem. So let's take this infinity norm, so constraint that infinity norm is less than epsilon. Let me walk you like quickly through these technicalities. So basically this says, okay, for every coordinate, the displacement must not be larger than epsilon, and then we have linearized loss function. So this is like constraint maximization problem. To solve this, we need these standard steps. For example, we could say we will represent this constraint in the form of a penalty function, which works like this. So we add the constraint multiplied with the Lagrange multiplier lambda. And if the constraint violated, then this bracket becomes positive. And then this minimum here over non-negative lambda of this non-negative product goes to the minus infinity. And then this is like a hard barrier for this outer maximization problem. So the maximum will not be attained when this part becomes the minus infinity. So the only case when this does not become the minus infinity is when this bracket is negative, so that when constraint is satisfied, and then this inner minimum is 0. So the lambda is 0 in that case. Okay, so we rewrote this constraint as this penalty, and then we could do we can swap minimum and maximum because this is convex in the lambda and concave in this x variable. So we could swap it to the minimum of maximum, and we could solve the inner maximization problem in delta x. Now, what I did also here, I squared the constraint. So instead of this constraint, we could square the both sides, so it doesn't change the constraint, but it is kind of convenient then for finding the stationary point after we swap. And the stationary point says this, that the step must be proportional to the gradient, but the step length is to be determined. And the step length is determined from the constraint. So if the objective how is it? Yeah, we were linearizing the function, so the objective is linear, and we are solving over some convex constraint set. Then this maximum has to be attained at the boundary of this set. And then so we are solving for the equation that the constraint is satisfied as equality. And then we determine the step length as this, and substitute back the step lengths. This gives us, okay, so it will be the epsilon, the size of this ball, and then direction of the step divided by this Lagrange multiplier, which proportional also to the gradient. So then the gradient divided by absolute value of the gradient is just sine of the gradient, right? So then this is our fast gradient sine method. If we take a different norm, it will be not sine, but something else, right? So, but we could do this sort of things. Yeah, we could like turn this into iterative attack. So instead of linearizing once, so the linearizing is an approximation, right? So if you want to really find the best adversarial perturbation, we maybe don't want to linearize the function. So we would like to solve really for the maximum, maximize the loss under the constraint that we don't go away from the original input image more than epsilon. And then we could solve this by kind of linearizing iteratively at each step. So before I was mentioning, okay, you could do this fast gradients and method with projecting on the constraint set. So here we could be kind of iteratively linearizing by keeping this constraint all the time in the maximization. So every iteration would be guaranteed to stay within the constraint by design. So maybe that would be more efficient. And we can solve this, I mean, similarly. So after we linearize, then we could treat this constraint optimization problem similarly and solve that. So we could have this iterated method, which would be refine, make the attack stronger. And we could have also targeted attacks. So if you like to, for the network to classify as some given class, so want to classify this cool bus as ostrich, you can find such a noise, or you want to classify this, what's that, I don't know, a dog as ostrich, you find some other noise. So you could do that. What's next? This was before we had like a fixed input and we were optimizing for the perturbation for that specific input, how to disguise the network to make a classification different or to predict the target that we want. Then somebody came and asked the question like, okay, can we find a single fixed noise pattern to spoil the classification of any input? And yes, they found, and they were available in diversity. So you take one of these patterns, like so for example this one. So this is showing only the noise, right? So if it is added to the image, like it is added here to this image, and you don't see after it is added, or it is added also to this image. So the same pattern can be added to all of the images, and then this mostly confuses the network, so it spoils the performance of the network. And they were testing also this on like cross model. So you find such a universal adversarial pattern for one architecture trained like VGG model, and then you go and try to fool the other networks with this exactly the same pattern. So, and then they were looking at this Fulling ratio, which is the percent of images that change the label after the perturbed. And then, okay, so it was, of course, the highest Fulling ratio was if you find the pattern for VGG network and apply it to VGG network. But then if you apply it to the, yeah, I don't know what's the x-axis and y-axis. So suppose then you apply then the CafeNet. So this pattern that you found has nothing to do with CafeNet. But if you apply it there, it also like has high probability of fooling that network as well. Yeah, and that's interesting. So that tells us something, right? So it tells that it's not so much specific to the particular neural network, but it could be something related with this class of architectures that we are working with the models that make these big linear combinations and then apply nonlinearities in general. I guess it would be true that the more similar the architecture is, then the more transferable these adversarial patterns. I don't know about that really. I think this is all ImageNet. So all of them trained on ImageNet. So this is 1,000 classes, 1 million images.
Semantic segmentation, it also works there. So I think people observe it all over different problems. So must be something there. But
yeah, the data comes from the nature. So you took lots of data. There's not really something specific and wrong with the data or lacking in the data. Yeah, okay. You asking maybe will this adversarial pattern transfer if you try to, I don't know, go segment medical images. It yeah, maybe. So maybe it's yeah, maybe not so well, right? But we would expect that there would be also adversarial patterns, and if the network is similar there, then maybe it will actually be also significantly affecting that network.
I think that was the question. How much the similarity of the network architecture plays a role, or how much the data set plays a role.
Yeah, indeed. But you see here, these networks are quite different. Yeah. Yeah, maybe. Yeah, but so in this field, it was, I don't know, thousands of works in this adversarial domain. After it has been discovered, people jumped on it and they tried all kinds of attack, like perturb only 5 pixels, but with an unlimited amount of perturbation. Do something with traffic science, with this and with that. I don't know all these results, and eventually there was, you would think, okay, once the problem is discovered and people jump on it, then it got solved. But this one somehow quietly stayed and went out of focus for the research. It seems so, but it stays there. So the the clip models and these more recent representation learning models, they are still somewhat vulnerable to adversarial attacks.
Leah, then like my intuition why this happens is that, I mean, just imagine fully connected network, yeah? So you have like, in order to produce one output in it, you have to somehow use all the inputs. So if you change them a little bit, like it's like there's so many degrees of freedom there. So even like small changes influences the output. So in some sense, it could be expected that this is like so sensitive. Yeah.
Well, that's the same argument as the lifting example from before. Like in that lifted space, a small change might be a very big change, like to the final header classifier.
So my guess was like, if you, but I wasn't able to prove it yet. I don't know if there is like such paper. Like if you make it sparse, I think like people can show that it's more like robust to noise and stuff like that. But I haven't seen paper like doing it for adversarial attacks. Maybe there is one. I'm not sure, but maybe there you can get some robustness. Maybe.
Somehow with this pattern, through this convolutional architecture, and maybe many of these models share this initial layers of this convolutional architecture, or in general they are convolutional, then these things which would result in, like, if the filters had sensitivity in this direction, so with the natural image that would just average out, but with this specific structured response, some activations are amplified, and so it causes some high activity. Yeah. Okay. Then we can talk about adversarially robust learning. So okay, what we can do to adjust the learning such that this is not happening. So yes, so in one intuitive idea is that you could just during the training, you could just try generating these adversarial samples and including them during the training to make sure that the training, to make sure that the classification works correctly as you like for both the original image and for the adversarially perturbed image. And to formalize this a little bit more conceptually, you could say the following. So we're gonna consider the following training problem. So we can look at the expectation of the loss over the training data, but then we want to minimize not only the expected loss, we want to minimize the expected worst case perturbation loss, right? So it has this illustration that around each data point you kind of place in the box and you're asking the network to predict correctly not only this point but also including all of the points in that box. So this box corresponds here to this delta ball in this formulation. And then if this was a linear classifier that was classifying the original data, with these boxes it cannot do this anymore. So it is not a solution to this problem. And the solution to this problem would be something like this red curve that sort of keeps the margin really in the input space as we would like. Yeah. By changing this optimization problem. Now you see minimizing this, where we have inside here a maximization over ball. It's kind of minimax problem. And the thinner problem, it does not necessarily have a unique minimum or a single maximum. It could be multiple different maxima because this loss function is nonlinear, and so who knows. But in principle, we could solve this somehow by this doing approximated by one step of this optimization, like the fast gradient sign method, or by iterative attack to solve this more accurately. And to solve this then this optimization, one interesting mathematical result that helps with that is this Dunskin's min-max theorem. What it tells us? It tells us that if you have a function which is a maximum of some other second variable of some other function, then if this maximization is unique, if it has unique maximum in Z for a given x, then the derivative through of this f function is just the partial derivative of the phi function at the maximizer Z. So you don't need the chain rule. So this maximizer Z, it depends on x, right? But you don't need to differentiate through this Z bar, through the maximizer. And like it is quite obvious in some basic examples. For example, so suppose you have like a Licker ReLU, right? So this is maximum of alpha x x. What do we do if x is here? We know, so this is one linear function, another linear function, and our function f is this one, but it is maximum of these two. So if the input x was here, we know that the maximizer is this function, so z is discrete here. So like this, z equals 1, z equals 2. And we only need gradient of this linear function. So if x is here, then we only need the gradient of this function. We have some problem if x is here, so here the maximizer is not unique. It's either z1 or z2. But in this case, it's still either of them is okay for optimization. So we have some subdifferential here, and that works as well. Then maybe it is less obvious in the continuous case. So if you have this phi that depends on both x and z, and it's somehow continuous function of two continuous variables, then maybe it is like less obvious. So it is kind of non-trivial fact. Then actually, what you need is this. So you don't need to compute z. It is a function of x if you like write this maximizer. And it could be a differentiable function of x, but you don't need to differentiate through this dependence. That's what this is in this case. Okay, and then yes, so then our algorithm for this adversarial robust learning could be something like this. So we take quite naturally, right? So we take some batch of examples, we find adversarial perturbations for all the examples, and then make a gradient descent step on the mini batch of these perturbed examples only, right? So using this rule, so we look at the loss at the perturbed, with this perturbation at the perturbed examples. Yeah, maybe some practical considerations apply to this. So this theorem, it's valid if you can optimize this exactly. But if you start approximating, so if you linearize this loss, then this is not exact. So then maybe something will be spoiled, and then this will not hold exactly. So it is what they showed experimentally or observed experimentally is that it helps if you do this iteratively. So if you just not make a single step on this inner maximization, but do it iteratively, then that helps. And the other practical aspect is that okay, we now require in the neural network to do like a substantially more complex job. So it might need even more capacity from the network to fit the data, including all the adversarial patterns. And
So could it be that the job is simpler because it doesn't need to focus on those aspects which are like distinguishing these lower level stuff?
it is, unfortunately, so something in the architecture of the neural network is such that they so they have these degrees of freedom to react to these adversarial patterns. And there is a big diversity of these adversarial patterns. So it's not like in this box you find one adversarial pattern, make network robust for that, and then you're done. No, there would be then in some other direction. So it will stick in out in the other direction. It will.
What I was saying is like, okay, if you prevent it to the network, I mean, you are saying it's difficult, more difficult task. I'm saying like
Yeah,
you are preventing the network to focus on any kind of classification in these dimensions, sort of.
yeah.
So eventually maybe easier. I mean, that's the question of the relevance.
Yeah, but at the same time, like the practice seems to be such that there are many of these directions. So if you prevent it in one iteration, you prevent it from bad classification in one adversarial direction. In the next iteration, it will be some completely different adversarial direction, which still spoils that.
In this scheme, you were like iteratively like summed in different directions.
Yes, but it makes your optimization slower and harder, and yeah, it could be. Yeah.
Might be that maybe there is a simpler solution, but like there's only like one small area where there's a glue, which is like
Maybe it implicates the landscape or
yeah.
whatever.
Would you please close this siren? Yes, it is. It is similar in many aspects to the other learning problems, like in general in deep learning problems. So happily we found some architectures which are easy to train. So they very quickly they train and generalize quite well. If you want to achieve some properties through designing the loss functions, this is typically like ways harder. So we could then, so if you want to improve generalizations through some appropriate loss or appropriate regularization, this then slower and harder. It seems so, and maybe in this case it's also like applies. But nevertheless, so it was helping to improve the robustness to the adversarial attacks. I do not show you the graphs how robust it becomes after you do that. So it becomes more robust. And it has also some additional interest in effects. So one effect is that let's look at this. So if you look at some intermediate features of the neural network and try to visualize which features are most active or have the high gradient for which neurons the gradient of the loss with respect to that neuron is high, then you could construct such a visualization. And in this case it was not nice, but after this training with adversarial patterns, this visualization becomes much more nicer, which tells something like, okay, there are less of the spurious features firing, which are then maybe in this network the effect is averaged out and cancels off. But in this network which was adversarially trained, they are not even firing. So there are less of these spurious features gets activated. And the other effect is that it seems to be like positive with respect to landscape of your optimization problem. What they show in this plot is the kind of conceptual illustration. So if you have some loss function, and then there was like a sharp minimum that without doing any regularization, you would find this sharp minimum. And if you here go over this function with the filter, which at each point it computes like a maximum over the ball, then you would get such a blue function. And this blue function, then if there was a wide minimum or flat minimum, then its value will likely to be preserved at a low level. If it was a sharp minimum, then its value will rise, and so this will be maybe a local minimum, but not a global minimum anymore. And then if you optimize such filter rate function, then you would be likely finding this point, which is the flatter minimum, which is sort of more stable to perturbations. The only issue with this, and they observe something in practice, right? Like, so if you do this adversarially robust training, then if you try to somehow evaluate these landscapes of the loss function, that you do see effects like this, that you are finding some flatter local minimum in some sense. But there is inconsistency here because this picture is in the parameter space, whereas the filter is in the input space of the images. So it is like you speak about the flatness of the local minimum with respect to the change of the parameter in the parameter space, but the method was actually filtering in the space of the images. And let's correct on this by considering the other work, which directly suggests to, okay, let us now filter in the space of the parameters. So maybe forget about the adversarial patterns, but let us try to regularize by saying that we will make a perturbation in the space of the parameters, like an adversarial perturbation, if you like, in the space of the parameters. So how this works, so this is the setup. We have a predictor that depends on the parameters, some training data, and the training loss function, which is the empirical average of the loss. And we want to find the flat minimum such that the loss, if we perturb the parameter, then the loss would stay small, right? Not only it is small for the theta that we found, but we want to find such theta that even in the neighborhood of it, the loss is still small. And how it is formulated. So it's again formulated as such optimization problem that you want to find the minimum, so to minimize in your parameters, but the loss function is now internally it is maximized over this adversarial perturbation, but now in the parameter space. And there is some regularization added to this, as quite usual. So this is adversarial perturbation over weights, if you like, right? Not the input images, but in the weight space. And in the case of this work, it was motivated also, they show a generalization guarantee, which is, so they say that the test risk can be upper bounded by such filtered loss with maybe some bound that decreases if this filter radius increases. So it was kind of motivated by this theoretical consideration that the more you filter, then the better generalization guarantee you have. And then, okay, let's now in practice, let's choose some regularization and some filter ball relevant to that and solve this. And the practical implementation is kind of also similar to what we've discussed before, but they went like a slightly different path. So they did not notice this property with the Duncan's theorem. They were saying, okay, we want first we solve this inner maximization problem, and for the L2 loss, okay, for the L2 ball here, the solution would be given like this. So it is in the direction of the gradient, but the length step is rho, right? So you divide the gradient by the length of the gradient, and then you multiply it with the size of this ball. So it is on the boundary of the ball in the direction of the gradient. But then this is a function of the parameters. This perturbation step is itself is a function of the parameter. And what they are saying that you need to compute the gradient of this whole loss in the network parameters. Then you have to do the chain rule. So you need to differentiate through the loss function and also differentiate through the dependence of this adversarial real perturbations through the theta. And then we were saying, this is possible, but it will involve, because this step, this adversarial step, it involves the gradient, and differentiating the gradient will result in the need to compute the Hessian of the loss function. It is somehow still possible to compute the vector Hessian products, but maybe not convenient. And in the end, they say, okay, we test this, and in practice, we also test this. Just here, forget about this dependence and do it like we did before with the Duncan's theorem. So just ignore the gradient of this step, how it depends on the theta. And I think it's something interesting is also like happening here mathematically. So this Duncan's theorem, it would apply here if there was no regularization, for example. So if you were able to exactly solve the inner maximization problem, and we would be wanted to minimize then the same loss function without the regularization, then that theorem would apply. If we make here an approximate step, then it does not apply anymore. So you don't have exact maximizer. If you have a regularization, it also doesn't apply anymore. So it's something to worth considering and thinking how these things work. Anyway, so they end up with this kind of approximation approach, which is very similar to the adversarially robust training. So in the picture, it is doing something like this. So this is our current weight parameters. The normal gradient descent would go here, right? So in the direction of the gradient to the next point. What they are doing, so they first going into the opposite direction to maximize the loss, right? This is the adversarial step in this parameter space. And then compute the gradient of the loss at this point. This gives you this blue direction. And then apply this step to the original point. So it ends up in this space of this sharpness of our minimization. So it's kind of going along the gradient of our loss function, but the gradient is evaluated at some other point, at the point of the like this adversarial example. Yeah, and that also improves also various things. Generalization performance, test performance, maybe, yeah, it depends how you measure generalization. I'm not sure if that improves robustness to adversarial patterns. I should have checked that. No, yeah, I don't know. Like if you wanted to come back with this. But yeah, so this is like related techniques. You could do this adversarial perturbations on the input space to make the network more robust and try to make it generalize better. You could make it on the parameter space. It's also possible to do it on the activation space. So you add some adversarial perturbations to the activation values, which generalizes over adding it to the input only. Right? So that if you make it robust to perturbations in all of the activations, then it is then as one consequence of that, it would be also robust to the perturbations in the input. So there are these possibilities. Yeah. So that's about the defense side, maybe. How effective it is? It is, at least for this adversarial robust cloning, but maybe not fully. So at some point, with a little bit more noise or a little bit stronger optimization techniques, there are still some vulnerabilities, I guess, remaining. Okay, so then what remains is maybe some fun part. What other adversarial attacks are there, and what other interesting things are there. So this work was about adversarial patches. So like, okay, so you have some neural network, and it is this, and with high confidence it classifies banana. Good. Then you place an image of a toaster next to this banana. Now the network was trained to predict for one object in the field of view. Now you have to, what it's gonna do? Yeah, okay, it is predicting a little bit of the toaster, and still quite confidently, highly confidently banana. But then they place like this smaller patch with some specific stuff in that, and this is becoming like super confident toaster, and no banana anymore. So what is going on? What they are doing? Or maybe let's discuss together. So how could you, so you are allowed to create any content of this patch. How can we find the patch that would be adversarially spoiling the network?
We would calculate the same way we train the network. We just swap now we calculate the gradient with relative to the input and not to the parameters, basically. And we say that we want, like, if it was some one-hot encoded like training samples, we would just say that everything is a banana or toaster.
I don't know if it is the same. It sounds similar. To what they did and to what I was asking. Like you have some original image, and then you as a kind of you construct the input to the network in such a way that at some random position you are placing the patch. And the patch, it is what we are going to learn. So this is our perturbed scene. And we are placing it in the natural images in the whole of our training data set. And we're going to optimize this such that wherever it occurs in the natural images and for all of the images, it would maximize the loss. And then you learn this, right? And then what you learn is the examples of that are this. And then when you show such a patch, and this is in the real world, right? So this is now like somebody showing it to the camera, maybe at somewhat different angle. So maybe here you also need to kind of be rotating this a little bit to make it fool the network in regardless of how it is rotated. And then you show one of these, and then the network will not see banana, but it will see toaster or the goldfish or the other stuff. Yeah, and then this can go further, right? So then somebody created such a pattern and printed it on the pullover. And then this guy is not detected as a person, so. And they have like the advertisement to this, that it was like stylish pullover, great way to stay warm in the winter. And it features something, adversarial pattern that awaits most common object detectors. Maybe, okay, I don't know details, but probably it was some, so they probably fooled the YOLO architecture, and I don't know how well it is fooling all variants of the detectors. But yeah, so he's staying tall here in front and big, but yet he's not detected completely. And then like there is now, you have a wide diversity of the fashion tools and camouflaging things, like the anti-face detector t-shirts, the glasses. So these glasses with some specific pattern on the rim, they were making some person identification to these guys in the person identification, so that this guy was recognized as Mila Jovovich if he was wearing these glasses. And this guy has some other setup. I don't know what was that exactly. And here it's like this is advertised as invisibility pullover. So you pull it on and then you got invisible. And yeah, so this is like a variant of this. So somebody is detected and the guy next to him is not, because he is wearing this pattern. Or you can have like a full dress when the system will see some giraffes or some other animals in here quietly walking, but no people. Do I have more? No, I don't have more. So that's the end of the story. Any thoughts to discuss? Oh, good then. So then tomorrow you will have a lab and you will try add some adversarial attacks, and then try also like some visualization techniques, so to see what is to get a better grip on what the activations and the gradients, what this tells us about the functioning of the neural networks, or at least a way to visualize something in neural networks. Okay, thanks.
Meeting at work, sorry.
All right.